Hello, this is Lakshmikant Tiwari. Today we are going to learn STM32 F7 programming using a Keil MicroVision. STM32 F7 have a Cortex M7 microcontroller, a most recent microcontroller released by the ARM. Here you can see it has a micro SD card, Arduino ports compatible to the Arduino UNO. Here the quad SPI flash, and it is the SRAM, and here itself it is a Cortex M7 microcontroller, and line connectors here, and the audio input and the output jacks, and there are also the two microphones here, and this is LCD 4.3-inch LCD TFT touch screen. So we will program it using the Keil MicroVision. If you don't have Keil MicroVision, you can download it from here, the keil.com. So you need to download here the Keil MTK ARM. It will take a little bit time. Wait here, and you fill your details here, then click on the submit, then it will lead you to link where you can download a Keil MicroVision and then install it, and then you can continue to watch this video tutorial. So I have already installed the Keil MicroVision on my computer, so let me open it first. Just wait, it is opening here. Keil MicroVision 5. When it will open a first time, it may open a default project here, or it may go a blank here, and also it may prompt you to download some additional files. So that is the pack installer. Okay, it will open pack installer by default very first time. So you need to first refresh it. You can refresh from here or go into the file and refresh it, and then it will enlist all the available devices which supports the Keil MicroVision. So click on the boards, and then go to the ST Microelectronics STM32 F7 board. So it is the F0 board, and STM32 F7, let me find it. F7, no, it is SN. Yes, here. So it is the STM32 F7 board, and then you will have STM32 F7 DFP package here, and then update it and download it. Okay, in the first time when you open your Keil MicroVision, it asks you to install it and also install some supported files. Okay, and if you already have, just update it if it asks to you. Fine. After installation and the updation every files here, then come to the project and open a project. Okay, so open a project. You can come to the local C drive. In the root directory Keil MicroVision 5, into the ARM, in the pack folder there is a Keil folder, and here you will find all the examples which are already installed on your Keil root directory. So we are looking for the STM32 F7 board. Just go on, come to this point. Okay, this is the project. All the example projects are enlisted here, and this is the Cortex microcontroller software interface standard, and here some documentations are there. Okay, it won't open here, because of that we are looking for only these files, and there are some drivers and the flash MDK files and the middleware supported files and some utilities. So just open a project here, and then the STM32 746G discovery, and come to the example, and here you can see the ADC board support package, DAC, DMA, I2C, power, SPI, timers, UART, everything is enlisted here. So open a ADC. So in the ADC channel, ADC folder, there is only one examples are there. So this is the ADC regular conversion using a DMA, direct memory access it means. So open MDK ARM, there you can find it is a MicroVision 5 compliance project.uvprojx file. Open it. So it will open into the read-only mode. That means you cannot modify any instructions or any lines of code here. Just click on OK. We will see later how to modify these codes. Okay, so just try to understand the basic file systems and other things regarding to STM32 F7 board. So this is the known as the project window, and this one is the editor, and these are the menu bar. Okay, so this folder have all the drivers supported to the BSP discovery board, and here it has the startup files, and here it has a doc file. The doc file explains what these examples will do. Fine, you can read these descriptions. You will find very comfortable to understand this code. And here it is a hardware abstraction layer. Here it is a hardware abstraction layer drivers. Fine, the RCC core clock reset and core clock here, UART, ADC, Cortex related files, and RCC extended files, I2C, ADC, everything are enlisted here. And in the driver there is only one system STM32 F7 files, and into the examples you can find the main file here. Okay, in the main files code is written for actual code. The main C program is written here. So it includes the first of all that the main.h. So the main header files are here, which includes all necessary header files and the definition files. So it includes the two necessary header files, STM32 F7 hall and the discovery header files, and also it has a related definition file related to the ADC and the DMA. And let's come back to the main.c file here, and here you can see the ADC handle type definitions. The ADC handle, before try to understanding all these codes, first let me explain you some basics about the ADC of the STM32 F7 board. It has a 3 ADC on board, in fact on chip. So all 3 ADC can be run into the parallel, ADC1, ADC2 and the ADC3, and there are 19 channel ADC, and only 16 channels available to the user, and 2 channels are internally connected with some peripherals, and also ADC clock can be controlled using the pre-scalers. It has a 12-bit ADC channels, and there are a total 16 channels which are available to the users on the chip, but on the board there are only the 6 channels available to the user. And also it supports the continuous mode and the discrete mode, DMA supports, and also the 8-bit resolutions, the 10-bit resolutions. And also it has a successive approximation type of the ADC. So as you know, the successive approximation type of ADC takes 1 clock cycle per bit. So it has a maximum resolution is this 12-bit. So it will take at least the 12 clock cycles to convert into the 12-bit resolution mode, and there are 3 clock cycle into the conversion. So it will take a minimum 15 clock cycle to convert a 12-bit ADC channels. This is the ADC handle type definition. It is a structure, and now we are defining a new type of the parameters, that is the ADC handle. And ADC handle will contains all the information regarding to ADC, such as the channel, such as the bit resolutions, scan mode, discrete and the continuous modes. And this is the just a 16-bit variables which will hold the ADC converted value, and the system core clock configuration which will configure the core clock of the STM32 F7 board, and it is the error handle user functions which will handle the error if error occurs during the programming execution of the program, and memory protection unit configurations and the CPU cache is also enabled there. So let's come to the main program. So now the one here, this structure will configure the ADC, and this structure will configure the ADC channels, and it will configure the memory protection unit, and this one will configure the cache unit. Hall initialization will initialize the every necessary peripherals on board on chip which are required to initialize the ADC and the boards. And the system core clock configurations, here these are the private functions prototypes, and these are actually we are calling the functions from here. BSP LED initialization is board support package LED initializations. LED1, there is only a single LED, that is the green LED. It will initialize that green LED into the digital mode output, and then you make configure your LED, that's mean toggle low or high you can make as you wish. And now come to the ADC handle structure. So the ADC handle dot instance, this is the ADCX. So what is the ADCX? It is defined into the main.h. So the ADCX is the ADC3. You cannot convert it. I am trying to edit it, but it is not editing it. Because of that, it is only the read-only mode. So here you can see it is a logged file, so you cannot edit. So this is the ADC3, and here it is initializing the ADC clock and the DMA. So the ADC3 is at the GPIO-F multiplexed, so we have to initialize the GPIO-F clock also. Okay, and here it is forcing to the ADC reset, and then we are releasing the ADC. Fine. That means we have defined here everything into the main.h files. And the ADC pin is the GPIO pin 10, that is the GPIO F. So it is pin number 10 of the GPIO F, and this pin is the corresponding to the channel 8 of the ADC3. In fact, it is also channel 8 of the ADC1 and the ADC2, and channel 8 is connected with the DMA channel 2 stream 0. Okay. So, and other things here, the scan mode conversion is disabled, the continuous mode is enabled. It means it will start the next conversions as soon as it will complete a current conversion. So, and the discontinuous mode, obviously it will be off. Because of that, the both of these conversions are dependent on each other. If one is enabled, another one will automatically be the disabled. And the data alignment will be the right alignment. It has a 16 bit registers, but our ADC is only the 12 bit, so we need alignment. So it is right alignment, that's mean upper 4 bit will be the 0 0. Fine. And the DMA continuous mode request is always enabled, so it will always request to the DMA to transfer the data from ADC to memory into the RAM. That means, so the DMA is a direct memory access. We will make some other tutorials on the DMA in the very detail, but let me tell you very basics about the DMA. DMA is specially used for high processing. Because of that, the DMA is itself a processor which will transfer the data from the peripheral to the memory, and the memory to peripherals, and memory to memory. So here ADC is the peripheral, so it can transfer direct data from ADC to the memory, that is the RAM, without the intervention of the processor, so that the processor can work another task simultaneously. So in the very next instruction, it is initializing the ADC. And if ADC will initialize successfully, it will return HAL OK, hardware abstraction layer OK. Now the another structure is the sconfig. So the sconfig is we will configure the channel. The channel number is the 8, and the rank 1 is the second most priority of the ADC. The highest priority is the 0, it is the rank 1. Sorry, it is rank 1, so it will convert first. Okay, it is not a priority, I am sorry. It is rank 1. That's when you are converting into the group mode, suppose that you are converting 5 channels, channel 1 to 5, you can define here the rank, which channel will converted next. So the rank 1 means the ADC channel 8 will be converted first. So here there is only one channel, so obviously it must be the rank 1. And ADC sample time is 3 clock cycles. As I have already explained you, the 12 clock cycle will take to convert a 12 bit, and the extra 3 clock cycles, so it will take a total 15 clock cycle to convert a ADC. And then here it is configuring the channel of the ADC, and then it will check whether it is okay or not. And then finally here we are starting the conversion process using a DMA. So DMA will automatically convert the ADC value, and it will store the value into the corresponding address of the ADC data registers, which are cited into the RAM memory. And then finally into the while one, we are looking for the ADC converted value. If value is greater than 2700, then it will make LED 1 off, and if it is greater than 2700, then it will make LED 1 on. Fine. And all these codes are the system generated codes. Okay, we will see how to generate this system generated code, and these are the initializing the system core clock, and this part is error handler user function, where you can write your own function to see if error occurs. So LED 1 will blink at the frequency of the 1/20 milliseconds. So that means it will make, I think, 50 hertz. Okay, the LED 1 will blink at the speed of the 50 hertz if error will occur there. So halt delay will provide a delay into the millisecond, but it is not very accurate, but you can use it, halt delay. Fine. So it is providing a 20 millisecond delay here. And here it is Hall ADC conversion callback. So it is if transfer, that's mean at a ADC transfer complete, so it is a interrupt based ADC. When a ADC conversion will complete, it will come to at this point, and then it will make LED 1 as a high. And this one is the USART failed. Okay, and you can also add your code here to handle this USART failed code. Memory protection unit explained here everything, and after that the cache CPU is enabled here. Fine. So this is very quick tutorial to do use of the ADC. As you know, board doesn't support the channel number 8 of the ADC 3, so we cannot use this ADC channel 8 on the board. Because of that, there are only the 6 channels available to the board, channel 0 to the channel 6, channel 0 to the channel 5, and unfortunately this is the read-only file, so we cannot modify it, obviously. So we cannot test this file onto the board, but definitely we can test it into the debug mode. Okay, so from here we can enter into the debug mode, but let me explain you what is the debug mode. Into the debug mode, you can execute clock by clock your instructions, and you can see inside the processors, inside your ADC and ADC clocks, everything you can monitor into the debug mode, and also you can generate their corresponding assembly code inside there. And also let me explain some other things here. So these are the icons from the build, and here it will rebuild all the files into the project files, and from here you can load your code into the board, and before loading the code you have to build from here. Okay, now it will build the code. Just wait for some time, and build output will be produced here. Okay, here you can see it is the ARM compiler. It has been invoked the ARM compiler. Now it is compiling every files there, and from the edit you can only save and open a corresponding only one file, but not a project. From a project you can open a already available project. Fine. Since it is compiling, that's why all the others are hidden. Okay, all options are hidden here. Just wait for some time since it is compiling. Wait. Okay, so it is here a 0 error and the 0 warning, and total code size is 8.828 kilobyte, and the read only data is 528 byte, and the read write data is 28 byte, and other data are the 1172 bytes. And here you can go into the option of the target, but you cannot save it as it is a read only mode. And here it is a target device. You can see the STM32 F7 board, F7 microcontroller, and these are some features about the microcontroller which are on board. Into the target, it is using a 12 megahertz crystal oscillator, but then it using a PLL and the FLL. It is overclocking it to the 216 megahertz. That's mean 216 megahertz, which is the board frequency. and into the output you can create a hex file and all other debug informations, and library also you can create. Into the C you can see it is already defined here some definition files such as use hall drivers and use STM32 F7 5666 and use STM32 discovery, and the optimization is the level 3, which is maximum level of the optimizations, and there are some include files here. And here it is a linker, okay, which will use the memory layout from the target dialog, and into the utility and the debug mode. Into the debug mode we will debug it using the ST-Link debugger. And to the setting you can go here, just verify all these settings. Into the port it must be the SW serial wire debugging, and the max clock is 1.8. Flash download, here the flash algorithm must be selected, STM32 F7 1 MB flash, otherwise you won't be able to flash your device. Fine. So now enter into the debug mode. From here no ST-Link is detected, because of that my board is not connected with my computer. So let me connect it. And how you can verify whether your board is connected with your computer or not, just from here you can come here and into the setting you can see no ST-Link is detected, and I am inserting my board, and just wait, I have inserted it. Now just refresh it one more time. See, ARM core site serial wire DP is detected. Fine. So now we enter into the debug mode. Just wait it. Now it is programmed, verified. See, here it will start from here. Now as you know we cannot see the ADC data on the board, but you can see the ADC data into the debug menu. Just go into the view and the system viewer, into the ADC here, it is the ADC 3. Fine. So here you can look into the inside your hardware. So as we know, the at the power up all the ADC peripherals and other peripherals are already reset, so everything is the 0. We need to set the control register 1 and the 2 and the status registers, then we will be able to see the data into the data registers. Here it is a 16-bit data registers. So first let me execute it. So you can execute these instructions one by one, one instruction by one instructions, and it is a corresponding assembly code generated here. Okay, so these are the some step in control lines here. So using this control lines you can go into the inside a function, and it will execute one line completely, and from here it will you can come out from a function. So we will use this step over. So in step over, ADC configure type is sconfig. Okay, sorry, by default I have clicked this one. Just come out with this function. Okay, now it is executed. Come to this one, cache is enabled, hall is initialized, system core clock is initialized, LED is initialized here. Now the ADC 3 is selected. Fine, clock prescaler and everything is selecting it. Just wait it. Yes, now it will initialize the ADC 3 here from here. Now we have set the every parameter into the structure here. Now it will initialize the ADC from here. Okay, here you can see it is initialized. Control register here, ADC control register 2. Fine. The continuous mode of the conversion is enabled here, and DDS is enabled here, and every all other things are the 00. Fine. And when the parameters, when the value will change, it will show into the blue colors. Okay, now it is initialized. Now it will initialize the channel. Fine. Here now you can see it is initialized the channel, and the status register, see the ADC is start. Fine, ADC has been started. Now come to the next point. Fine. Now it is DMA requesting. Let's see converted value. See here the converted value is a 040A. Now some other values also you can see here into the stack. While what are the other values are already into the stacks. So these are into the stacks. Okay, yes, config and everything is into the stacks. So channel number is 8, rank is 1. Okay, and if you want to see the some variable such as converted value you can obviously see here, but also you can see a converted value in the variable. Wait, that is here. See, copy it and click on the watch window. See here, it is 1035. You can see into the hex also, so you can display into the hexadecimal, and also you can display it into the here decimal value. Fine, so you can go next by next. See here, if the value is changing every time. Since the value is very less and we cannot provide any input to the channel 8, so that you won't be able to see the LED as a blinking. Because of that, it is already written if the value is greater than 2700, then it will make the LED off, otherwise LED on. So it won't work here, and obviously we cannot modify this program. But I hope you have gained some knowledge how to use the Keil MicroVision and already available projects. So thank you so much for watching, and into the next tutorial we will see the UART codings and the DMA.